All right, guys, in class last time, we've been talking about Newton's first law, which is the law of inertia. And I want to talk about this in a little bit more detail right now. We'll begin and get into the second and third laws. But the first law was the law of inertia, and we went into this in some detail. But you might remember the basic summary of the law of inertia, the way we could sort of summarize this just as a reminder, was we said that an object does not accelerate unless there's a net force. Okay, so in other words, let's just write it this way. Objects, we said, don't accelerate unless a net force is applied. Apologize for the messy handwriting here. I'm working with a new tool, new system here, so just trying to get used to it. So this is the basic concept of inertia. We had fleshed this out in some detail. We had this big long sentence that we tried to digest, which was something like an object in motion will remain in motion in a straight line at constant speed, and an object at rest will remain at rest, all unless acted upon by a net force or an outside force. And since we know what acceleration is, since we have now an understanding of what that word is, right? We know what acceleration means. Since we know what acceleration means, we can sum up Newton's law in a little bit more of a succinct way by saying objects don't accelerate unless a net force is applied. So let's make sure that we understand what that means when we say objects don't accelerate unless a net force is applied. Well, this means that an object when there's no net force will not, in terms of accelerate, will not speed up, slow down, or turn. Those are really the three ways that you could accelerate, is to speed up, slow down, or turn. So anytime you've got an object that's not speeding up, slowing down, or turning, the net force on that object is zero. And this is the idea that I want to kind of lay out a little bit more today. It may sound obvious. It's an easy thing to say, but as I mentioned in class, I really do think that this is fairly non-intuitive, and I do want to try to get into it in a little bit more detail now. So, what I actually want to do, I want to think about, for right now, I only want to think about cases where the net force is zero. We're going to, in a couple days, think a little bit more about what happens if there is a net force. But for right now, let's just confine our discussion to the case where net force is zero. So this is called equilibrium. Equilibrium is defined as the case where there's no net force. In terms of an equation form, we write F net is equal to zero. And again, this is called equilibrium. That's sort of the fancy term for this idea, equilibrium. So I want to go into equilibrium in a little bit more detail. So let's imagine now so again, I know I just said this, but equilibrium, what does it mean? It means the object is not speeding up, slowing down, or turning. So it could be at rest, but it could be in motion, right? It could be moving, and if it's moving, it has to be moving in a straight line at constant speed. All right, so let's say I've got, I don't know, we could just have, here's the floor, and maybe we've got this block or box on the floor right here. And I'm telling you now that this box here is in equilibrium on the floor. So the net force is zero on this box. Now that doesn't mean there aren't forces at play, right? We know there are forces going on here, right? We've got gravity is acting downwards. There's a gravitational force. I'm going to express this a little differently than I did last time. The gravitational force on an object, that's known as the object's weight. If you think about it, you know what weight is. Weight is the force of gravity acting on an object. You have weight, I have weight, because of gravity. If there were no gravity, there would be no weight. So this is weight, and later on, you don't need to know this right now, but there's an expression for weight. It's m, mass, times g, the acceleration due to gravity. So we'll talk more about that later. So we've got weight. Weight is pulling down, but you might remember this. We said this in class. There's another force pushing up on the block, box, whatever this is, that's canceling that weight force out, and we call this the normal force. So I'm going to write F, normal. And the normal force, just a little bit of a word on what the normal force is. The normal force is a force that's always perpendicular to a surface. In fact, the word normal is sort of an old mathematical term for perpendicular. So the normal force is normal not in the sense of like usual or everyday. It's normal in the sense of being perpendicular to the surface. So in this case, perpendicular to the floor here. So here we have this block sitting on the floor, and indeed it's an equilibrium, right? These forces are equal. This force and this force are equal to one another. They're equal and opposite. They cancel out. Net force 0. Now, by the way, if I look at the diagram I've just drawn here, there's a term for this kind of a diagram. This kind of a diagram, this is called a force diagram. It's a diagram where I've drawn the object and I've given all of the forces at play. This is a force diagram. So I've just drawn a force diagram for the block. Now, if you look at this force diagram, if I just drew this for you and I asked you, can you conclude, is the object moving or is the object at rest? I want you to think for a minute what you would say to that. Can you conclude, do you know, based on this picture, is the object moving or is the object at rest? You may be, as many students are, tempted to say, well, there's no net force acting, so the thing must be at rest. And this is an easy temptation to have, but I want to remind you that the fact that there's no net force doesn't mean the object has to be at rest. It simply means, again, that the object must not be accelerating. It could definitely be moving, but if it's moving, again, at constant velocity, straight line, constant speed. So you can't conclude based on the picture. You can't really conclude if it's at rest or if it's moving at constant velocity. But let me just tell you, why don't I just say, let's assume that this object is at this moment at rest. And but maybe now you want to try to move this thing. So you start to push on it, right? And you're going to give it a push. You're going to push it this way. You're going to push it with some force P. That's your force. You're pushing on it. But maybe there's quite a bit of friction on the ground here. Maybe there's some stickiness. Maybe it's a heavy box, and that push P is not enough to get this thing moving. So it's not moving. You're pushing on it, but not enough to get it going. So you might wonder to yourself, well, how is it if I'm pushing it forward? Why doesn't it move? Well, there's obviously another force which is counteracting your push. There's a force acting this way, and that's the friction force. And this friction force must be, again, equal and opposite to your pushing force. Those forces must be equal. Because you're pushing, but the thing hasn't accelerated, right? I told you, you pushed it, but it didn't move. So, again, we're still in a scenario here where the box is in equilibrium. Okay, there's no net force. Now, obviously, you can imagine a situation where you push harder and harder and harder, and you push such that you overcome this friction, and the block begins to move. Right? That could clearly happen. We'll discuss what happens when an object begins to accelerate. We'll discuss that next week. But for right now, I want to sort of think about this force diagram as an example of equilibrium. So this block right now is in equilibrium. Again, based on the picture, you can't tell for certain if it's moving or not, but you can say based on the picture that the object is not accelerating. Let's think about another case. This is a slightly more complicated case of equilibrium now. Let's imagine I've got a ramp. That's not a particularly straight line. So we're sort of adjusting to my new tools here. Let's see if we can do better than that. Oh my God, that's worse. One more try. I guess that's going to have to do. So we've got this ramp here. There's a ramp, and maybe now I've got a block on the ramp. Here's this block that's on this ramp, right? And I want to know what's going on with this block. Well, let's say there's a force, weight, mg, weight is acting down, right? Weight is always down. It's always towards the center of the Earth, right? Because gravity is always pulling down towards the center of the Earth. But what other forces are acting? Well, there's going to be a normal force again. And the normal force, I want to point out what the normal force, again, what that's all about. The normal force is coming from the surface, right? The ramp is pushing on the block. And the fact that it's a normal force, that just means that the force is going to be perpendicular to the surface of the ramp. In other words, it's going to be this way. Perpendicular to the surface of the ramp. 90-degree angle from the surface of the ramp. So this is the normal force. F normal. But you can see now this is a little bit different because the weight and the normal force are not opposite one another. There's an angle here. Those are completely opposite. That's not 180 degrees opposite. So what's going on here? Well, we could think about it. It might be helpful to take that weight force and to split it up into pieces. You can see that some of that weight force is acting this way down the ramp, and some of the weight force is acting this way into the ramp. Can you see that? This is the component or piece of the weight that's acting parallel to the ramp, and this is the component or piece of the weight that's acting perpendicular to the ramp. And these forces right here, these are equal and opposite. Okay? These are equal and opposite. So based on this picture right now, this block is not in equilibrium because these two forces are canceling out, but this guy right here isn't canceled out. So if this block is going to be in equilibrium, there has to be another force. There's got to be a friction force acting backwards like that. And now maybe that friction force and that component of the weight cancel out. And now we've got a case again where the net force is 0. Okay, so this block now is in equilibrium. Again, I'm going to point it out again. I feel like I'm repeating myself, but you don't know based on this. You don't know based on the fact that the net force is 0. You don't know if it's moving or not, but you do know that it's not accelerating. So this is another case of equilibrium, okay? Hopefully that helps you understand a little bit more about the normal force, again, perpendicular to the surface. Slightly more complicated example. Let's do another case of equilibrium if we can. Alright, what are we going to do? Let's do one more here. Maybe we've got... Here's the ceiling. And we've got a weight hanging from a couple of ropes on the ceiling here. So maybe this is the weight right here. It's hanging by a couple ropes. Now it's really, really ugly lines. I got to get better with this new method here. So you've got this weight hanging from these two ropes, and it's clearly it's in equilibrium, right? It's just hanging there. It's not moving. So there are forces acting on this weight, right? We've got weight acting downwards. It's the force of gravity. But what's holding it in place? Well, there's also forces from these ropes, right? These ropes are exerting forces. There's a force that way and a force that way. Okay? These forces on the ropes, these are called tension forces. This is F sub T for tension force. A tension force is a force that's conducted along a rope or a chain or a string, whatever. That's a tension force. And the way this works right here is that the total upward force, this total upward force produced by both of these tension forces, this force is equal to the weight. Okay? That's why this thing's in equilibrium. The total vertical force produced by these two tensions, the tension in this rope, let's call that rope A, and the tension in rope B, both of those ropes are exerting some upward force, and the combined upward force of those two ropes is counteracting the weight. By the way, these two ropes are also exerting tension forces to the side like this, and these two tension forces are also canceling out, which is why it's not accelerating in the side-to-side direction either. So once again, this is another case of equilibrium, a case of net force equal to 0. So just to review this is all cases. Ooh, we didn't need that. These are all cases of Newton's first law, and we've got instances where objects are not accelerating because there's no net force being applied. That's all we're discussing right now. The idea that net forces are required to produce acceleration. So flesh that out a little bit more with this concept of equilibrium. We made a series of force diagrams. This is a concept. Drawing these force diagrams is a concept that we're going to delve into in greater detail in class, in our next class. So hopefully that's helpful, and we'll practice this soon. All right, guys. What I want to start with. This video is really supposed to be about Newton's second law, but before we get there, I do want to just once again go over some of the details about Newton's first law. This is a tricky law, and I think we saw it in class going over these force diagrams. It's a tricky concept. So I'm going to kind of review some of what we've talked about again, and I'm hopeful that if I keep going over this, the more we sort of come back to it, the more likely it is to stick. So I've expressed here at the top, this is, of course, the statement that we've been using to summarize Newton's first law, right? Objects only accelerate if there's a net force, right? So if there's a net force on an object, it'll accelerate. If there's no net force, it won't accelerate. And remember what we mean by this. You know, we've said this before, but let's remember this. Accelerate means it's either speeding up, slowing down, or turning. So if it's not doing any of those three things, then the net force must be zero. In other words, all the forces added up must yield zero force. So we have, I've started off with A and B. I want us to start off here. I've actually drawn a force diagram for you. And I want to think about how you would describe the motion of the object indicated. So let's think about this rock in part A. So we can see here's the rock, and it's on the ground, and we have two forces here. We've got the weight, the force of gravity pulling down, and then we've got the normal force from the ground pushing up on the rock. And those are the only two forces present. And once again, I want to think about this. What does this mean about the object's motion? First of all, can we conclude, is the object at rest or is it in motion? Is it moving or is it at rest? You might remember we said in class today, and I said in a previous video, that based on this picture, based on this force diagram, you cannot make any conclusion about whether or not the rock is moving. Okay, it could be moving or it might be at rest. What we do know, the one thing we do know, I've attempted to draw this so that these two forces are equal, by the way. What we do know, since the net force is zero, we know that the object isn't accelerating. There's no acceleration. That's what we know. So if it's at rest, it's going to stay at rest. If it's moving, it has to be moving in a straight line at constant speed, right? It can't be doing any of these things. It can't be speeding up, slowing down, or turning because there's no net force and therefore no acceleration. Part B, now what we've got is we've got a situation where we've got the weight pulling, gravity pulling the object down, the normal force pushing it up. Those are equal and opposite. And now there's some pushing force. I don't know, maybe there's a foot here that's pushing this rock along. And then there's a frictional force that's acting opposite from the pushing force that is also equal and opposite. So once again, I might ask, what can you conclude about the motion of this object? Well, the only thing, once again, that you can conclude is that it's not accelerating. That's the only conclusion you can make. In both cases, the net force is zero. So in both cases, the object is not accelerating. Once again, it could be at rest, or it could be in motion in a straight line at constant speed. Tricky concept, but again, hopefully going over these helps. I've got a couple more here to review from class today. Now what I've done is I've drawn the object. I haven't indicated the forces present, but I've given the scenario, and I want to see if we can come up with the what forces I should draw in this case. So part C here says we've got this rock on the ground, and it says that it's moving at constant velocity, and it says that there's no friction. So what forces are acting? Let's start with the easy ones. We know, try to make that a little bit straighter. We know that there's gravity, right? That's weight. We know that's present, always there, assuming we're on Earth. And we know that there's a normal force up. I'll just call that N for now. So those two forces are present. But it says here that the object is moving at constant velocity and there's no friction. In other words, no friction means, let's assume, by the way, let's just assume that the rock is going this way. It's going to the right. No friction means I don't get to draw an arrow backwards. Right? There's no force holding this rock back from moving. There's no force to the left. The question is, should I put a force to the right? So we went over this in class, but this might be the single most sort of illustrative example of Newton's first law, this particular case. Students frequently want to put an arrow in here, and they want to say, well, look, the thing's moving to the right. And I know from my everyday experiences that anytime I want an object to move to the right at constant speed, I got to push it. And you'd be right. In your everyday life, you need to push objects to keep them moving at constant speed. But the reason for that is in everyday life, there's always friction. You don't experience no friction. You don't experience that ever, right? There's always friction. But if there were no friction, according to Newton, no force would be necessary. In other words, in this particular case, I have to get rid of this force here. Because since there's no friction, let's see if I can erase that properly. There we go. Since there's no friction, then there's no forward force necessary. If I put an arrow there, it wouldn't be moving at constant velocity, because if I had a force arrow going in this direction, that would mean that there'd be a net force, the object would be accelerating. In other words, it would not be moving at constant velocity. In other words, this is the picture. Done. Okay, we went over that in class, but I think definitely tripped some students up, so it's good to revisit it. All right, let's take a look at D here. Now we've got this rock, and we're told it's slowing down due to friction. Slowing down due to friction. So slowing down right away. What does that mean? That means we're going to have an acceleration. It's slowing down. We're going to have an acceleration. We're going to have a net force. So once again, let's start off with the easy ones. Weight acting down. Okay, normal force is up. Those are easy. Now, what to do from here? Well, I know that there's friction. Let's once again, let's assume that the rock is going to the right. I know there's friction, and if the rock is moving to the right, the friction force is going to be this way. Friction. Okay. Now, do I need an arrow in this direction? Well, it doesn't. The problem doesn't specify. It doesn't look like there's anything pushing it forward, so I might not put an arrow there. This picture is sufficient as I've drawn it, right? These two guys are going to cancel out, and then the net force is the friction force. It's acting backwards, and so there is a net force now, and we've got slowing down, right? If there's a net force, there should be acceleration, and that seems to be what we've got here. So it's all well and good. You could, if you really felt compelled to, you could put a little arrow here, but you'd have to be sure to make the arrow this way shorter than that arrow, right? It would have to be shorter, because if it was the same length, then the net force would be 0 and there'd be no acceleration, and the object would be moving at constant velocity. It wouldn't be slowing down. All right, so that's a little bit of a review of what we had previously talked about, but this is, again, I know that's a tricky concept, so worth spending a little bit of time going over it again right now. Okay, I promised you that we were going to move on to Newton's second law, that was going to be the main thrust of this little module. So let's do that. Let's get to Newton's second law. Newton's second law is really, this is going to feel good because conceptually it's not that hard. Okay. Now that we've gotten through with Newton's first law, Newton's second law conceptually is going to be a lot easier. In fact, Newton's second law is really just an equation. So Newton's second law, what it addresses is what happens if there is a net force. Okay. So what if there is a net force? What happens then? Well, we know the short answer is it's going to accelerate. But what exactly is the relationship between acceleration and force? How are they connected? Okay, so let's imagine that we've got a scenario where there is a net force. What's going to happen here? So actually, why don't we, before I even get into the law, why don't we think of a scenario where, let's imagine we've got a surface here, and let's imagine for right now it's a frictionless surface. And here I've got this object, this rock, and it's frictionless, so there's no friction. Okay, and let's imagine I give this rock on the frictionless surface. Let's imagine I give it a push. So I'm going to give it a push here, this direction, a push P, and I'm going to say that I'm pushing here. Let's say I'm pushing with 32 newtons. Okay, and I know based on this picture, right? I didn't bother to draw this, but let's remember, of course, that we've got weight down, and we've got the normal force acting up. Those are still present. These are equal and opposite. They're going to cancel out. There's no friction. So I'm not going to draw an arrow to the left because it's a frictionless surface. So in this case, we've got a net force. The net force, switch my colors here, the net force, F net, is 32 newtons. Okay, so I've got a net force. This thing is going to accelerate. This rock is going to accelerate to the right. But by how much? Can I determine how much it's going to accelerate? Is it going to be a little, a lot? Maybe I could come up with a number. It'd be nice to know. Is it going to accelerate at 1 meter per second or 10 meters per second? I'd like to know. And to think about this, before we define Newton's second law, let's think about what else might be involved. Obviously, the force matters. I think it's pretty obvious that if I were to push this harder, it would accelerate more. If I were to push it softer, it would accelerate less. But there's another thing that matters, and that's how big this thing is. I haven't told you anything about this. Is this like a grain of sand, or is this like a bowling ball, right? What does it weigh? How heavy is it? How much mass does it have, this thing? That's also relevant. You probably want to know this, right? If I were to kick a soccer ball and then kick a bowling ball with the same amount of force, the soccer ball is going to accelerate a hell of a lot more than the bowling ball. So clearly mass matters. So I need to know something about mass. So let's give this thing a mass. Let's call this thing, let's say it has a mass of, let's say 8 kilograms. I want to point out right away, and we're going to deal with this probably in a later video, but or in class, mass is not weight. Let me just make a parenthesis element about this. Mass is not weight. We're going to come back to that. But for right now, let's just indicate that distinction. Mass is not the same thing as weight. So we've got this 8 kilogram rock. It's being pushed at 32 newtons. The question is, what's its acceleration? Well, Newton's second law is going to come to bear here. And basically, without further ado, let's go into Newton's second law. Newton's second law relates acceleration and force. And basically, the way I'm going to write it is, it says that the acceleration is equal to the force on the object divided by the object's mass. That's Newton's second law. Okay, it's basically just an equation. Frequently, you'll see this rewritten in other books, and sort of the famous formulation of it is actually to rearrange this thing to solve for m. So to solve for f. Usually, you'll see this, or you might hear this: F equals ma. It's the same equation, just sort of rewritten. I sort of like writing it this way here because it gives me a little bit more intuition for the relationship between acceleration and force, and then acceleration and mass. And you can see, I think it makes sense, but since F is on the top, if F gets bigger, A gets bigger, right? If the numerator of the fraction gets bigger, the value of the fraction gets bigger. Down here, if I look at M, if M gets bigger, right, A gets smaller. If the denominator of the fraction gets bigger, the overall fraction gets smaller. And that makes sense, right? I kick a soccer ball, it accelerates more than if I kick a bowling ball, right? The bowling ball has more mass than the soccer ball. So let's apply this to our problem up here, right? We want to know the acceleration. Well, I know the force is 32. I know the mass is 8, so I can say that the acceleration of the of this rock here, right? I'm continuing this problem right here. The acceleration of the rock is 32 newtons over 8 kilograms, and that's going to equal 4. What's our unit for acceleration? What is it? Meters per second squared. Final answer. That's the acceleration of the rock in this case, based on this force and this mass. I mentioned that this conceptually was going to be a little bit more straightforward, and I think it is. I think it's a little bit easier than that first law, right? A equals F over M. The only little bit of vocab I'll throw at you, I just said that as F gets bigger, A gets bigger. One gets bigger, the other gets bigger. The way we talk about that is that's a direct proportion. Let me write this vocab out for you because you might hear this again. What we would say is acceleration is directly proportional to force. And then we'd say acceleration is inversely proportional to mass. Well, inversely wrong, inversely. Well, you know what I'm trying to say there. So this is just a little bit of vocab. You might remember that from math class. Directly proportional, meaning if F goes up, A goes up. Inversely proportional, meaning if M goes up, A goes down. Hopefully that makes sense. Okay, I want to introduce one more new concept and then try one more problem here. I want to think about a special case of F equals ma. So this is a special case. And that's weight. What is weight? Okay, well, what is it? It's not mass. It's related to mass, right? Something with more mass on Earth would have more weight, but it's not quite the same thing. We said weight is the force of gravity. Weight is a force. Okay, so weight is the force of gravity. So if I look at our equation F equals ma, weight is a force. And the weight of an object is equal to the mass of the object times A. Well, what's A in gravity? Well, A is the acceleration due to gravity, g. Okay, so this is our special case of F equals ma. Weight can be expressed mg. And that comes directly out of Newton's second law. Right? The force is weight. The mass is the mass of the object here, and the acceleration is the acceleration due to gravity. So weight is a type of force. It's the force of gravity, and here's how we express it, mg. Taking that in consideration, I want to apply that to a case. What if I had my rock now, and maybe my rock is falling through the air, okay? And what if I have this rock, and I'm going to tell you that the rock has a mass of, let's say, 5 kilograms. And it's falling through the air like this. And there's air resistance, right? Air is going to resist this thing. It's trying to fall. Air is going to try to push it back up. So let's say that there's a resistance force here, resistance force R, and let's say that that's 19 newtons. And I want you to find what's the acceleration of this rock based on that information. Okay, so we've got this 5 kilogram rock falling through the air and encountering a resistance force of 19 newtons. So why don't we start by doing a force diagram, right? We've got mg, that's weight down. Try to be a little bit neater. This is mg, that's weight, and this is R, resistance. So don't get confused. I used to say W here. That used to be W, that used to be weight, right? But now I'm calling this mg. This is weight. It's nothing new. I'm just calling weight mg now, because that's the equation form. And I know these values, right? I know that the resistance force is 19 newtons. And I can calculate mg now, because I know mass is 5 kilograms. I know g is 9.8, so mg is 5 times 9.8. Right? G, remember this, g equals 9.8. That's the acceleration due to gravity. So mg is 5 times 9.8. That's 49 newtons. Okay? So now I've got to go ahead and calculate my acceleration. I can do it now. The acceleration is force over mass. Well, what's the force? Well, the downward force here is 49 newtons. But there's an upward force of 19 newtons, right? those are opposite one another. So the force is going to be 49 minus 19 over the mass, which is 5. This is A equals F over M, right? That's what I've done here. This is F. This is M. A equals F over M. Okay? Just express the net force as 49 minus 19. Okay, well, let's evaluate this. What's 49 minus 19? That's 30 newtons over 5 kilograms. Divide that out, and we get 6 meters per second squared. Okay, so we can say that this rock here is now accelerating. It's accelerating downward, has a downward acceleration of 6 meters per second squared. We just use Newton's laws to figure that out. Okay, hopefully that's helping you out. Again, the point of Newton's second law is it really allows us to describe what's happening when there is a net force. Okay, and if there is a net force, there's going to be an acceleration, and this equation right here gives us that relationship. So we practice one here on a flat surface, and then we practice one here for an object falling through the air. This case here, this particular case, we're going to deal more with in class next time. We're going to do some practice involving this case. So I hope that made sense, and see you next time.